Alright, let's continue here with a little bit of applications of the standard normal distribution and the normal distribution. So once we start doing this, you're going to see why it's good to use standard normal distribution and what makes it easy and stuff like that. So as this graph here shows you, most of our measures are, well, as we talked about before, we're always talking about the area under the curve with continuous distributions. It's never going to be a single spot, it's going to be a region, right? Often, when we're looking under the normal distribution, we go the area to the left of a specific point, because if you need the area of, say, x and a little bit less than x, where my cursor is here, then you can do x minus this whole thing minus where my cursor is minus the whole thing, and you'll get the area in between those two. I'll just draw it out here real quickly. So, that's horrible. And where did I put my pen? Here we go. So if we have another area x and x minus 1, and we want to see what this area is, well, we can do the original purple area minus this region here, and that'll give us that area in between. Well, what does this look like? How do we find out what those probabilities are, right? What is this region? Well, think about it with this problem here. We have mean of 63 and a standard deviation of 5. And this is the final exams for a statistics class. But notice all I really cared about was the mean of 63 and the standard deviation of 5. Why is that? Because, and well, here's the question, is greater than 65. It wants the area greater than 65. So from this, it's pretty easy to see that this is our image that we're going to create. We have a mean of 63, and we want to know the area greater than 65. But how many distributions are there that we have observed that we know with exactly a mean of 63 and a standard deviation of 5? Well, we could find out the area for this, for those specific numbers, every single time, or we can put it into a common language, a common distribution, the standard normal distribution, where, notice, this axis here changes, and just like in this problem, our axis is going to change and put it in a standard normal. Now, these z-scores, when we talk about the area under it, we know these z-scores. We find those in, fittingly, the z-table. This is just a little piece of it. Most of the values, will be closer to the bottom, but the way this works is if you have a z-score of 2.8, you're going to, negative 2.8, you're going to start here, and then these are the decimal places after it, and 2.8 would just be that. Negative 2.802, or 2.82, sorry, would be here. Negative 2.89 would be here. So that's how you're going to find it. And now what do these numbers correspond to? Well, we have, let me pull up a new slide here. Let's think. Negative 2.8 intellectually, just as a thought process. If we have 0, because we've now normalized our scale, there's no mu's here, and we have a z-score of negative 2.8, that's 1, 2, almost 3 standard deviations over here. And we're measuring, the z-score table gives you the area to the left. So what's the probability of being all the way over here? Really small, right? Well, let's go back, check the table. Sure enough, 0.0026. It is really, really rare that you have a score almost 3 standard deviations to the left of the mean. Now, that's why we skip back and forth, because, as long as things have a standard normal distribution, we can look at just about anything with this table. That means we could look at ACT scores, we could look at average birth weights, we could look at, just about anything. Anything that's normally distributed, we can translate into this and calculate the areas very quickly. And I'm going to, so for these example problems, I'm actually going to link to Khan Academy. Once again, I'll add his videos into the playlist, and he does a great job with these as well, and his website also has some great practice problems. So I'm going to stop here. I hope that makes that clear in terms of why we use the standard normal and the z-score tables. Yeah.